So yeah, hi everyone. My name is Tangzheng Lian. I'm here to present our recent work on fair domain generalization and information theoretic view. Yes, so this is going to be quite theoretic. So we have upload a manuscript archive as well. So we are interested in two topics. So the first one is domain generalization. So as we know, in real-world deployments, machine learning models often face domain shifts. So where the test data is coming from a domain that never seen during training. So this introduced two research paradigms. The first one is domain adaptation, which will assume that the target domain has some unlabeled data that's available. And another one is more challenging. So it's domain generalization, which will assume that the target domain is fully unknown. Instead, we typically assume that we have multiple source domain available, so we can learn domain invariant representations. The other topic is algorithmic fairness, or say group fairness. So group fairness aims to prevent the performance disparity across subgroups of data depending on the sensitive attribute. So as shown in this example, so the task is visual expression recognition, and the sensitive attribute is perceived race. So if the white faces are overrepresented in the training set and black faces are underrepresented, if you train the model on this imbalanced training data, you will observe a performance disparity between these two subgroups of data. And algorithmic fairness, also group fairness, is trying to minimize this performance disparity. So our research motivation is twofold. So the first one is that those methods that are working on domain generalization, they typically solely focus on minimizing the expected race, which is try to maximize the accuracy in the target domain. And they often overlook algorithmic fairness. As a result, those models that generalize well might still be unfair. And conversely, those fairness methods do not account for domain shifts. So the fairness achieved during training might not generalize to the unseen target domain. So we started the problem of fair domain generalization, which we aim to bridge these two problems together to simultaneously minimize both the expected risk and the fairness violations in unseen target domains. So here's an illustration of the problem. So again, imagine the task is to classify visual expressions. So in the source domains, we have different age groups as the domains, and the task of domain generalization is to generalize this classifier to an unseen age group. And at the same time, we also have this imbalance problem, which, like for instance, white faces are overrepresented in the training set, and black faces are underrepresented. So we also want to minimize the performance disparity between this subgroup of data. So before I dive into problem formulation, let's get familiar with some basic notations. So the calligraphy symbols here are the supports of the random variable. So the random variables are both these symbols. So X is the random input, and Y is the class label that's corresponding to the input. And DS is the source domain variable. G is the group membership given a sensitive attribute S. And DT is a unknown target domain that we want to generalize. The lowercase numbers are the realizations of the random variables. We have two assumptions. So assumption one, so we assume that there exists a domain random variable D, which follows a categorical distribution, and its support at least contains like two source domains and one unseen target domain we want to generalize. The assumption two is that we focus on the same sensitive attribute S and its group when moving from source domain to the target domain. So here's the problem formulation. So for domain generalization, it's quite traditional. So our objective is to find the set of parameters of a function f that can minimize the expected race in the target domain. Another one is group fairness. So we choose a group fairness based on a metric called equalized odds. So we also did another metric called equal opportunity, which is a special case of equalized odds that only consider the true positive rates. So EOD requires this conditional distribution to be identical. So here the y hat is the model's prediction, and y is the class label, and G prime are two different attribute groups. So on the level of PMFs, so this actually saying that so for every prediction, we want this conditional probability to be equal. And we're actually interested in minimizing the violations of these criteria, which can be quantified using total variance distance. And if we average the total variance distance across the multiple class and multiple groups, we can get this delta EOD, which is a multi-class and multi-group version of equalized odds. So we are interested in minimizing the delta EOD in the target domain. So it's conditioned on DT. So these are the two terms that we want to minimize. However, it's quite challenging. It's not straightforward because we assume that DT is unknown. So the solution is to derive bounds so that we can minimize the upper bound that relate to the source domains. So we derive two theorems. The detailed proofs are providing a manuscript on arXiv. So here I'm just gonna briefly go through. So for theorem 1 is the upper bound for the expected rates on the target domain. So we show that the first term is the expected rate in the source domain. The second term is a discrepancy in the distribution of the input space in target domain and a mixture distribution. So here this term is not parameterized and the TT is unknown, so we cannot control this term. And the final term can be is a mutual information term that can be decomposed by that can be further decomposed by the chain rule, which the mutual information between the source domain variable and y is actually a constant. It's not parameterized. You can estimate it from training data. So yeah, the takeaway here is that for algorithmic design, I want you to focus on the components of the upper bound that are both controllable and parameterized. So here are the two components. So the same for theorem 2. So we derive an upper bound for the EOD violation in the target domain. So the denominator is not parameterized, it's constant. You can estimate from the training data. The second thing is uncontrollable. The message here is that we should focus on these two conditional mutual information. We further give another theorem which will relate to the from risk minimization to mutual information maximization. So we prove that if the loss function is cross entropy, we have the following inequality, which the H here is the entropy, which is again is a non-parameterized constant. And we show that if you minimize the expected rates over the source domain, it's actually you're pushing up the upper bound of the mutual information between your model prediction and the true label condition on the source domains. So if we combine this insight with the takeaways from theorem 1 and 2, so we can have this nicely formulated objectives all based on mutual information. And we give another theorem 4, which is are the chain rules bounds. So in inequality 4, on the right-hand side is actually the two terms in our objective that we want to minimize. So this actually minimizes the upper bound of the mutual information on the left, which is like the last term of our objectives. So we can simplify this objective by throwing out the last term is redundant. And inequality 5 actually says, so the first thing is the first thing on the right hand side is what we want to maximize, and the second thing is what we want to minimize. So this actually push up the lower bound of the mutual information on the left, which is actually what we want for domain generalization. So what we want to maximize the mutual information between the model's prediction and the true label without depending or conditioning on any source domain. And the same here, so in inequality 6, we prove that the two terms that we want to minimize actually minimize the upper bound of the mutual information on the left, which is actually the mutual information form of the EOD, and it's not conditioned on source domain variable. So so we can generalize the fairness. So we have this formulation in theory that's address the problem of fair domain generalization. However, in practice, it's quite hard to estimate it. So we have several challenges. So the challenging one is that directly compute the model prediction is non-differentiable. So the typical solution is to replace the prediction by latent representations. So we decompose the F into two components. So the feature encoder and the classifier. So we replace the f theta x by the latent representations. So the idea here is that if you learn a representation that is fair or domain invariant, the classifier that applies on that application will also be fair and domain invariant. However, this introduces a second challenge, which is that so calculating the mutual information for high-dimensional representation is difficult, and it requires approximations like MINE, mutual information neural estimator. So the solution to this is that we can replace the mutual information with a differentiable dependence matrix that can capture both linear and nonlinear dependencies and also work well with high-dimensional random vectors. So here are the two options. So the first one is human space independent criterion called HSIC, and the other one is distance correlation, DCOR. So the objective of minimizing these two mutual information terms actually is equivalent to enforce the conditional independence of these two relations, which can be measured by DCOR. So we choose DCOR here so we have experience showing that so DCOR is actually the best for implementing our methods. So we show the experience in the later slides. So the other challenge is that so for implementing the DCOR, so I said here that the categorical labels fail to capture intragroup similarity in the way that label representations do. So I will explain. So the DS and the G in the DCOR in real world, they are typically categorical, and the ZE here is continuous. So to deal with this mismatch of distance calculation, so we introduce a domain and group encoder to represent them as latent representations, so that everything of DCOR can be calculated in the latent space. So we have discussed in theory like how to calculate DCOR, but we don't know the probability distribution of these random variables. So what we need to do is to give a finite training set and see how we can estimate it. So here are the empirical version of the distance correlation. So you can refer to the detailed calculation of the empirical DCOR in our appendix. So up to now, we have two pretty good estimates of the mutual information that we want to minimize, and the term that's left that we need to maximize. That so we can relate to the theorem 4. So this is actually the minimization of the expected rate in the source domain. So given a training set, it's just empirical risk minimization, so minimizing the average of the loss. And the challenge 5 is that, so as noted in many fairness literature, there's often trade-off between utilities and fairness. So this means that these two objectives are often in conflict. So the solution is that we formulate it as a multi-objective optimization problem, and we instead optimize for Pareto optimality. So to summarize, so here is the objective in theory. We have its empirical version, and we optimize for Pareto optimality. And the lambda here controls the utility fairness trade-off, and the gamma here is the regularization parameter that controls the source domain invariance. So training, in this framework, we have 4 parts of network to train. So we propose a 2-stage training pipeline. So in the first stage, we only train the group or the domain and group encoder to overfit the training set and freeze them. And they are discarded at inference time because we don't need them to make predictions. The only purpose of these 2 encoders is just to guide the feature encoder in training so that the representation learned can be domain invariant and fair. And in the second stage, we just train the feature encoder and the classifier to perform the main classification task. And another challenge in training is that, so for multi-objective optimization, we need to train a model from scratch for each lambda, which is computationally intensive. So we have a trick here. It's called loss condition training. It's actually, we learned it from a paper called YOTO, you only train once. You can find it on the internet. So the trick is, instead of just put the input x, we put an input pair of x and the lambda, so that the network can be conditioned on lambda as well. So at inference, we only need to just pass different lambda to the model as an input to yield a particular trade-off. So evaluation. So we have different lambda values, and we have different models to evaluate. So each so the I here refers to the solutions. We have n solutions. So each of them are measured by fairness criteria, EOD, and utility metric, the overall accuracy of the classification. So we can identify a set of dominating solutions and the non-dominating solutions, which is the Pareto optimal solutions. It's a Pareto front that is non-dominating. And because of there is a scale differences between the EOD and accuracy, so we need to normalize the Pareto front. And to evaluate the Pareto front, we use a evaluation matrix called, we use an evaluation matrix of hypervolume indicator, which is the, in 2D space is the reference point. So we choose a reference point. In 2D solution space is just the area under the Pareto front. We have another evaluation, which is the global criterion. So we choose the utopia point, which is the point that is too ideal to achieve, like 100% accuracy or zero fairness violation. And the optimal solution is the one that closest to the utopia point by L2 distance. So we run our methods across different data sets, different like multi-class classification tasks, which includes like Celebrity A, FNet, and Jigsaw. So Jigsaw is a natural language data set. And here's our results. So we compare with domain generalization methods, fairness methods, and fair domain generalization methods. Most often they are optimization-based methods. We can observe that so domain generalization methods typically have high accuracy but also large fairness violations. The fairness methods have a bit of improvement in fairness violations, but with huge sacrifice on accuracy. So fair domain generalization methods, they improve fairness quite a lot, but with minimal sacrifice in accuracy, with ours being the best. So here is the visualization of the Pareto front. So the shady area here is the HVI that I talk about. So the larger the better. So our method consistently outperform the compared baseline across data sets and evaluation metrics. So here's the emulation study. We talk about that we try mine, HC, and decoy, and we find decoy is the best. And we also have experiments on the number of source domains. We see that when we increase the domain speed, the source domain speed, our performance increased quite a bit. But this is at cost of extra annotations. So in conclusion, we define novel theoretical bounds in this problem, and we introduce a framework that can practically solve the problem while modeling the utility fairness tree-off through Pareto optimization. And we run experiments on both language and vision datasets to show the effectiveness of our framework. Yeah, that's all. Thank you.